other. All right. So if we can agree on that, then we should be able to agree on the following. If we define an integral as we have, is that when you integrate something, it goes from lowercase f to uppercase f, and then you plug in your bounds, and you plug in your top bound minus your bottom bound and subtract it. We agree that we've defined that. The question is, what happens if you take the derivative of both sides? Okay, so what literally happens when I take the derivative? All right, so on this screen, what I want you to do is notation how you would show that you would take the derivative. Prime doesn't work as well, so let's use Newton's method notation this time. So if I want to say I am going to take the derivative of this side, but if I do it to one, I got to do it to the other. So that means I will be taking the derivative of both parts of the other side as well. All right, so our question is, what happens to that? Well, I want you to think about the capital side. If I take the derivative of a capital, what's going to happen to it? Okay, it's going to go back to being lowercase again. Okay? Okay, it's going to go back to being what it was before. Okay? All right, so here's what we have. All right, if we do that, it is going to go back to what it was before. And so we take the derivative of the outside, so the capital F turns into a lowercase f. But the rules of derivative are that you take the derivative of the outside and then do what? Okay, but what do I do to the inside? Nothing, right? At first. I take the derivative of the outside, which changes it from a capital to a lower, but I do nothing to the inside. But then, because there are parentheses, I take the derivative of the inside too. And what's the derivative of b? Lowercase. Yeah, you can write db, not dt, but d, what are we doing here? dx, okay, and then minus. And the other one, the outside changes from capital to lowercase, but the inside doesn't. Oops, a. But then the chain rule requires me to do dA, dx. All right, so when you take a derivative combined with an integral, you end up back in the function that you started with. You end up back with f again. But the difference is the chain rule also applies, and so you have to remember the chain rule. That is key. That's going to be that's one of those. It's like, oh, not only do I have to remember my plus c, I got to remember my chain rule too when I do this. So let me show you how this works. If I take the derivative of the integral of the function sine, what function do I end up with? Right back to sine. I end up with sine. Okay, if I take the derivative of the integral of the function that starts out as sine, I'm going to end up right back with the function that ends up as sine. So the answer to this is to end up with the function sine. But what goes into the parentheses? Okay, what goes into the parentheses first? What's the upper bound? We said that it was the b value that goes in there, okay? So what goes in there? X. And then what do I have to remember to multiply by? D something, dx, and what's the something? X in this case, because that was the upper bound. Minus sine, and then what gets plugged in next? Pi. And then I have to remember it's d something, dx, and d what? d pi. Okay? Now, can that be simplified farther? Yes. Okay, how? dx dx is 1. Anything else? Okay, what's the sign of pi? 0. What's the derivative of pi? Okay, well, but the derivative of pi is also 0. Because pi is what kind of a number? It's a constant. And its derivative is going to be 0. So this whole thing is 0. And so my answer is simply the sine of x. Okay, let's try it again. Find the, yeah?
Why is it not like dt on the bottom of this one?
Because I wasn't taking the derivative with respect to t. I was taking the derivative with respect to x. Remember, it matters what you're taking the derivative with respect to.
t in the original thing? Why is it there?
Okay. You want to do it the long way? We do it the long way. No problem. Okay. All right. Well then, what is the antiderivative of sine of t? Okay. The antiderivative is negative cosine of t plus c, and the bounds are pi to x. And then we plug in those. Negative cosine of x plus c minus plus cosine of pi. Oops, I wrote plus 1 instead of plus c, my thing. Minus c, okay, the c's cancel each other out. Okay, so that's the antiderivative. So that takes care of the integral, but this is a two-part process, right?
Mm-hmm.
Part 1 was the antiderivative we just did. I'm just doing that for you. What's part 2? Take the derivative, right? Take the derivative of that. Where are you going to end up back at again? What's the derivative of negative cosine of x? Positive sine of x. And what's the derivative of the cosine of pi? 0, and you end up back at sine of x again. So what's the point? If you have both a derivative symbol and an antiderivative symbol at the same time, don't they just cancel each other out? So I'm trying to save you time. You don't have to do the antiderivative because this problem has both a derivative symbol and an antiderivative symbol in the same time. Okay, a derivative symbol and an antiderivative symbol cancel each other out, but you still have to deal with the subtraction, and you still have to deal with the chain rule, which in this case, there was a nice 0 for our chain rule. Okay? All right, so here. If y is defined as an antiderivative, but I am asked to find dy, then I'm finding a combination of both a derivative and an antiderivative. So what's the point of doing it? There isn't one. Save yourself the time if you can recognize that. Okay, so what will dy dx end up to be? Where will I end up back at? Sine. But what will get plugged into that? X squared is the upper bound. And then what will the derivative be? It'll be the d dx of what? Of x squared. What is the derivative of x squared? 2x, yeah. So let's just write it as that, 2x. Minus, and then it'll be the sine of the lower bound, which is the number 1, and then times the chain rule of what that lower bound is. And what will the chain rule produce in me in this one? 0. So I, again, have a nice, lovely 0. So I end up with 2x times, and I usually write the 2x part in the front, but it wouldn't be wrong if you wrote it with the 2x in the back. Okay. You just have to watch what the question is asking for. First semester, we were only asking for derivatives. The last couple days, last week and a half, I've only been asking for antiderivatives. These questions are asking for both a derivative and an antiderivative in the same question, and if they are, all that does is negate each other. And so I'm just trying to save you the work of having to figure both out because you end up in the same place. Okay, let's try another one. This kind of gets to Chloe's question from earlier today, if you remember what Chloe's question was. How are t and sine t related to each other in this problem? What's the mathematical pairing of those two? Their multiplication. It is called a product. If I was going to figure out the antiderivative, what would I need to know? I would need to know, how would I find out a derivative of that? If something that's a product, what rule do I use? Product rule, okay? If I'm asked to find the antiderivative, I would need an anti-product rule, which we don't have. But what's it asking you to do? It's asking you to do the combination. It's asking you to find the derivative. So let's see how this is going to end up for us. Okay, let's do the derivative to both sides. So I'm going to put d dx around the y side, and I'm going to put d dx around the x5 t sine t dt sine. So just make sure you do it to both sides. The definition of the derivative of y with respect to x is dy dx. The definition of the derivative of an integral that starts at bounds x to 5 is going to leave me with what?
Sine 5.
Close. Okay. What happens to these two things right here? What are they going to do to each other? They're going to cancel out. Okay. So I'm going to be left with not just sine something, but 5 sine something, because there's the t there. I'll be left with both of them. So I will be left with 5 sine 5 times what chain rule derivative? Not cosine. It's only the derivative of what's sitting here. That's the only thing that changes. The sign doesn't change. The multiplication doesn't change. It's still a multiplication. I use the number 5 and I multiply by the derivative of that, which is 0. Then I minus,
Sorry, just keep going on.
okay. Then I'm going to minus what expression? X sine x times the derivative of that part, which is 1. So the 0 is wiping out which part of it this time? The front part, okay? The front part. So I end up with the answer to this being negative x sine x is the answer. Okay, yeah, Izzy.
Okay, so then you would need to have a variable, or more importantly, x in the integral bounds, because otherwise they're just two constants and they would be 0.
Yes, yes.
Okay, why? I don't get it.
Well, if they were two bounds, okay. The antiderivative, if just think about, okay, let me just go over here. So suppose you had 7 to 11 of x sine x dx, okay? If you could do an antiderivative of x sine x, which you can't yet, if you could, you'd have the derivative, you'd plug in 11, you'd plug in 7, okay? What do you get when you plug in 11 to an antiderivative? You're going to get a number. What do you get when you plug in 7 to that? A number. And a number minus a number, still a number. So you're going to have a number. What would happen if you took the derivative of that, regardless of what the number is, what happens when you take the derivative of that? What's the derivative of every number? Is going to be 0. Right, so there's no point to doing a problem like that because it will be 0 every single time. At least one of the bounds has to be a variable.
Will like AP give us problems like that?
They're not going to waste their time with this, probably not.
Imagine that on a graph.
Okay, well, on a graph, from 7 to 11 is going to represent the area under that curve, and the area under that curve is going to be a number. And if you take the derivative of that, you're still going to end up with 0. The derivative of any number is 0. You got to have a variable, otherwise the derivative is going to be 0 every single time. At least one variable. You could have multiple variables, as we'll see on the next question.
Does it have to be x if you're taking the derivative of
With respect to x. Yeah, if it's going to be the derivative with respect to t, then the t has to be in the bounds. Yes, yeah, good, good. Wow, that's really good thinking. All right. Okay, let's try it again. All right, given one thing right now, okay, just what we're given, we're only given an integral. If that's all we're given, then I want you to actually do the integral. All right, so we're actually doing the integral this time. So 2x to 7 of 1 over 3t dt. Okay, the actual integral of that, what is the integral of 1 over 3t dt? Natural log of what? The absolute value of 3t, what else? What else? What else? Divided by chain rule 3.
oh my goodness.
I think I got the.
Because if you have 3 on the inside, you got it. Okay. And what will the bounds be? 2x to 7. Okay. And then plug in the 7. So you'll get the natural log of what?
It's 21.
21, do I need absolute values?
No.
No, but still over 3. Does that reduce to 7?
No.
Good job. Okay, then we'll have our plus c. And then minus the natural log of
Absolute value to 6.
absolute value
Yeah, 6.
6x. And I need absolute values. Why?
Because you want to
I don't know if x is a positive number or a negative number, so I need it. Over 3 and then minus c, which will eventually cancel each other out. Okay? That's the hard way to do that problem. It's hard. You got to remember the natural log, you got to remember the chain rule, you got to remember, you're plugging in. I mean, there's a lot to remember. Okay? It's easier to do the differentiate part. Because if I do the differentiate part, that means throw a d dx in front of 2x7, 1 over 3t dt. And when I throw a d dx in front of it, what does the d dx do to the integral? Cancels each other out. And what am I left with? 1 over, I don't have to do anything. I can just take the function 1 over 3
times 7.
1 over 3 times 7 times, that's the only part you got to remember. It's not just times 7. What's it multiplied by?
Times 1.
No, what's the derivative of 7?
Oh, 0.
0. Minus 1 over
3 times 2x.
3 times 2x times,
Times 6.
not 6,
2.
2. It's the derivative of these things. It's the only derivative you have to take are the derivative of the bounds. That's it. The derivative of 7 is 0. The derivative of 2x is 2. That's all you have to, that's what you have to remember. It's the easier part. It's the easier part.
Negative 2 over 6. Actually, simplifies to negative 1 over 3.
That's, yes. So the answer is negative 1 over 3x. All right, let's keep going. See if we can put this all together here. Find the tangent line. All right, so you'll recall from first semester that a tangent line requires 2 things. So hopefully in your head right now, you're thinking, okay, I need a point and I need a slope. So to find the point, we're going to plug in x equals 3 into what is given. And then to find our slope, we're going to plug in x is 3 into the derivative. All right, so let's see if we can do that. Let's find our point first. So let's plug in x equals 3 into what is given. And what is given is that equation right there. Okay, so 3 goes in for x. 1/2 of 3, or 3/2 would go in for that. So I'm just going to put 3/2 there. 1 over 1 plus t squared dt. And I'm going to actually figure this out. I know the antiderivative of 1 plus t squared is tan inverse plus constant c from 3 on the bottom and 3 over 2 on the top. So that'll give me tan inverse of 3/2 plus c minus tan inverse of 3 minus c. And you can use your calculator just to figure out the decimal value of that. So in radian mode, that comes out to be negative 0.267. So my point is 3, negative 0.267. All right, to find my slope, I need to plug x is 3 into the derivative, which means I need to figure out d dx of what was given. All right, and to find d dx, essentially the derivative cancels out the integral, and I'm left with exactly the same function I started with, but the bounds get plugged in. So it'll be 1 over 1 plus 1/2 of x squared. It's the upper bound plugged in, and I have to remember that the chain rule applies. That would be times half. Minus 1 over 1 plus regular x squared times the chain rule applies would be 1. And I am going to plug 3 into this. So that would be 1 over 1 plus 3/2 squared, still times the chain rule of half, minus 1 over 1 plus plain 3 squared times the chain rule of 1. And then go ahead and use your calculator to evaluate that value. So in radian mode, I get 0.054. So the tangent line, using that point and that slope, would turn out to be, in point slope form, y minus plus 0.267, and then the slope of 0.054, and then x minus 3. So it's something old, finding the tangent line using the point and slope, but something new, whereas we're starting with a function that's defined as an integral. All right, last one. Given a function, find the position, the velocity, and the acceleration. All right, well, we're given the position function, p of x. P of x is a to x of the function of t dt, which means we're moving along the t-axis, moving along the time axis. The velocity would be the derivative of a to t f of t dt. Okay, so now we have a derivative combined with an integral. So remember, the derivative will cancel out the integral as long as I remember to plug in the two bounds. So that will turn out to be f of the upper bound of t plugged in times the chain rule of the derivative of t, which is 1, minus f of a, the lower bound, times the chain rule of that, which is 0, which cleans up to be just f of t along the time axis. Okay. And then a of x would be the derivative of what we just got, dx of f of t, which is f prime of t, again, along the time axis. All right, so what do all these things mean and how do we evaluate them? So the position is going to be done by finding the area, because that's what this means. It means find the area. So if I need to find the position, then I'll be finding the area. For the velocity, I end up with this. That means, let me do it like this, that you're finding the y value, because that's what f means. F means you're finding the y value. And then when we end up with f prime of t, f prime means you're finding the slope value. So suppose overall you're asked to find the position, velocity, and the acceleration at time equals 5. So suppose that that's what you're asking. So the position at 5 would be the area up until t equals 5. So you calculate the area, and that's what that means. V of 5 would be the same as f of 5, which is the y value at t equals 5. And then a of 5 would be f prime of 5, which is the slope value at t equals 5. So previously, we've said the slope value means the velocity. That's only if position is defined as f, the original function. This time, velocity is the original function, and so the acceleration is the slope value instead. So I find in these physics questions that it helps maybe to, on the side, write down how everything is defined. How am I defined? Which one represents velocity? It's like in first semester when I said, this graph is position, and then this is how you read it. But then I switched it and I said, this graph is a velocity. How do you read that? So we're doing the same kind of questions now. We're just defining them more, instead of a graph, we're defining it as an actual function. And so you have to know by reading geometry and how to do that. All right, so we will talk extensively about this again tomorrow, and I hope you have a good rest of your night.